Hello and welcome to the lecture series on principles of electrical engineering. In this lecture, we will try to look into one problem, and we have got the circuit which is shown here, and the question is the switch S. This is switch S, so single pole double throw switch has been in position 1 for a long time. This is your position 1, okay, and at time t equals to 0, the switch is moved to position 2. This is your position 2, okay. So the question is, find IL as a function of time, t. Okay, so what is IL? I is the current which is flowing through the inductor. So we have got this circuit. We have got one inductor in the circuit. There are two DC supply, one of 100 volts, the other one is of 50 volts, and there are four resistors of different resistances, 60 and 50, 40, and here 40, and this inductor is of 1 millihenry. So the question is, switch which is earlier at position 1 for a long time, and then it is moved to position 2 at time t equals to 0. So you have to find out what would be the current that will be flowing through this inductor IL as a function of time. Okay, so let's start solving this problem. Now let me draw this circuit once more, okay, and this time when the switch is connected at position 1 for a long time. So in that case, we have this DC supply, and there's a resistor, and the switch is at position 1. This is position 1, and we have a resistor, and then there is another resistor here, and then we have an inductor. Okay, so important thing to note here is that this is 40, this is 60, this is 50, and this is of 1 millihenry. Okay, so the important thing to note here is that since the switch is in position 1 for a long time, that means now the circuit is in steady state. That means the current that is flowing in the circuit would be a constant current. Okay, so if that is the case, that means now the inductor would be behaving as a short circuit. Okay, so it means that if this is short circuit here, this has been shorted. Okay, so this is shorted here, so that means this resistor goes. So what is left is only this resistor and this resistor, and along with the 100 volt supply. So the current that would be flowing in the inductor, IL, so IL, let me call it IL 0, so initial 0 minus, basically just before the switch has been moved to position 2. So the current that will be flowing through the inductor is given by, it is 100, the voltage, divided by the sum of these two resistances which are in series. So the 100 divided by 60 plus 40, so that is 100. So this equals to 1 amperes. Okay, fine. Hello. Okay, so so the initial current, we have found it to be equal to 1 ampere, so we have to remember this. Okay, now let's proceed. Our next step would be we would look at this circuit, and basically we would try to find out how circuit looks when the position of switch changes to 2. Okay, so let me redraw the circuit again. So 50 volts, and this resistor is 60, then this is again 50, and we have got this inductor, and okay, there is a 40 volt, 40 ohm resistor here also. So this is 40 ohms. Okay, and now this is connected to this is position 2. So this is 40 ohms. This is your how much, 60 ohms. So this is 60 ohms, and this is 50 this is 50 ohms. Okay, this is 50 ohms, and this is 1 milliamp Henry. Okay, so this is the circuit when the position of the switch S moves from 1 to from here, and it moves to this position 2. Okay, now we have to analyze this circuit now. So this is the circuit for t greater than equal to 0. Okay, so to analyze the circuit, it would be easier if we can simplify it. So let's try to draw the Thevenin equivalent. Okay, so let's consider these 2 points as A and B, these 2 terminals, and let's try to find out the Thevenin equivalent of the circuit of this portion. Okay, so we are required to find out RTH and VTH. So for RTH, we basically we have to short circuit this source. So basically I would be getting this circuit. Okay, so this is point A, and this is point B. This is 50, this is 60, this is 40. So this is RTH. So RTH would be given by, so this 50 is in parallel with the combination of these 2 resistors. So 50 into 100 divided by 50 plus 100. R1 R2 divided by R1 into R1 plus R2. So R1 into R2 divided by R1 plus R2. Okay, so this gives me 50 into 100 divided by 150. So this cancels out, and this is 3, so 100 upon 3 ohms. So this is the equivalent Thevenin resistance. Now let us try to find out VTH. So to find out VTH, so let me redraw the circuit here for VTH. So we have got the current, the voltage source, and there is a resistor. Okay, and then there is again a resistor here, and one more resistor here, and okay, so this is point A and this is point B. I'm interested in finding out the current here through this resistor so that I can find out the voltage that would be appearing across A and B. So this is 40, this is 60, and this is 50. Okay, and this is let me see it. The voltage here is 50, So this is 50 volts. So the current that would be flowing here through the 50 ohm resistor would be given by I would be equal to 50 divided by 40 plus 60 plus 50. So that is 50 upon 150. So I get 1 by 3 amperes. So VTH would be 50 into 1 by 3. 50 is this resistance. So this equals to 50 by 3 volts. Okay, so we have obtained the resistance, Thevenin equivalent resistance, as well as the Thevenin equivalent voltage. So let me redraw the Thevenin equivalent circuit. So this was 50 by 3, and this is 100 by 3, and this is ohms, and this is volts, and this is the sorry, this is not a resistor, this is the inductor. Okay, and this is 1 millihenry. So this is a VL, the voltage across this inductor. So now this is a simple RL circuit, and we know that we can find out the response of this circuit quite easily. So the current that would be flowing, ILT, would be given by I so I infinity plus I 0 minus I infinity, this much times e to the power minus t by tau. The tau is L by R. So this is equal to I infinity. I infinity is the current that would be flowing in the circuit after a long time. So that means at that time inductor would be as good as a short circuit. If that is the case, then I infinity will be given by this voltage 50 by 3 divided by the resistance 100 by 3. So this is equal to 0.5 amperes. And we had already found out the initial current in the circuit I0, and we know that it is equals to 1 amperes. Okay, so that is okay. So we have found it out here. Yes, 1 ampere, you could see here 1 ampere. Okay, so let us now try to find out this expression. So I infinity is 0.5, is 0.5 plus I0 is 1 minus 0.5 again, 0.5, okay, so into e to the power minus t by tau. Tau is L by R, so this is into R. R is we have found it out, it is 100 by 3, so this is 100 by 3, and L is 1 milliohm, so 1 into 10 to the power minus 3. Okay, so let me write it down again here. So this is equal to 0.5 plus 0.5 into e to the power minus t